In this video, we're covering section 1.5 on linear equations, functions, zeros, and applications, and section 1.6 on solving linear inequalities. Here are the objectives for each section. And now we get into some definitions. So an equation is a statement that has two expressions on opposite sides of an equal sign. And in this course, we'll just be sticking to one variable. And to solve an equation just is to find all of the values of that variable that make the equation true. So just solve for the variable. The set of all solutions of an equation, because sometimes there could be more than one solution, is a solution set. So we have some examples here. We have 2x plus 3 equals 5. That's an equation. We have this example in the middle that has x's on both sides. We could have x's in a fraction like this, or we could have something like this. That's x squared plus 2x plus 3 equals 0. So a quadratic equal to 0. Any of these are equations. You can see other variables in here, but there will only ever be one variable at a time. They won't ever be mixed. So whenever we're trying to solve an equation, we have two principles that make that really easy. So first is the addition principle, which means if we're going to assume that a, b, and c are constants or expressions. So if we have something where a equals b, then we can add some c to each side and still have the same thing. We actually do this all the time. So for example, if I have x minus 2 equals 5, when I do that plus 2 to both sides, this is what that looks like written out, right? X minus 2 plus 2 equals 5 plus 2. So essentially, I don't change the problem if I do operations to both sides. And on this side, those two cancel, and I get x equals 7, which is why we do things like that. But this is the principle that allows us to do that. Now, looking at the multiplication principle. Again, if I have a equals b, then I can have a times c equals b times c. So I can multiply both sides of an equation by some number. So for example, if I have 1/4 x minus 1 equals 3, I can multiply both sides of the equation by 4. Like this. And that's a nice choice because then as my 4 gets distributed to my two different values, this is pointing all the way over to that little 1, the 1 right here. The 4 times 1/4 gives me just an x minus 4 equals 12. And all of a sudden, this problem has become much, much simpler. And so I can even add 4 to both sides and immediately get x equals 16 on this kind of problem, right? So the principles we typically will combine and we choose special values, but as long as we do operations to both sides, we're good. Now, specifically, linear equations in one variable are equations that can be expressed of the form mx plus b equals 0, where m and b are real numbers and m is not 0, so there must be an x value in there. And as usual, we recognize linear equations by looking for things where there's no exponent on the x. So for example, 5x plus 1 equals 0. That's a linear equation. Now on the right-hand side, we also have a linear equation. X plus 2 equals 3x minus 4. Because you see, I can, let's say I add 4 to both sides, and I get x plus 6 equals 3x. And now I'm going to subtract 3x from the left-hand side and the right-hand side, and I get x minus 3x, which is minus 2x, plus 6 equals 0. So even this equation above can be written with equals to 0 as soon as I move terms to the other side. Now, we have something called equivalent equations. And equivalent equations are when two equations have the exact same solution set. So for example, if I have 2x plus 3 equals 5 and 2x minus 1 equals 1, and let's solve for x in each. So I subtract 3 from both sides, I get 2x equals 2. And so I divide by 2 on both sides and I get x equals 1. So x equals 1 is my solution to 2x plus 3 equals 5. Now on this other one, I'm going to add 1 to both sides, and I get 2x equals 2. Again, I divide by 2, and I get x equals 1. So these are equivalent. Now for a perfect non-example, we look at x squared minus 3x plus 2 equals 0, and 2x minus 1 equals 1. Well, maybe just take my word for it, but both x equals 1 and x equals 2 are solutions to this quadratic equal to 0. But x equals 1 is the only solution to this linear equation, 2x minus 1 equals 1. Therefore, they are not equivalent equations because x equals 2 is not in the second solution set. So they have to be totally the same. Okay, so now you're going to see problems like this where you have fractions in there. Something like 3 over 4 times x minus 1 equals 7 over 5. And we have a trick that we can use to actually make this problem a little bit easier and get rid of those fractions. So I'm going to use that multiplication principle where I can multiply both sides of the equation by a number and hopefully simplify something from there. Now, I can multiply both sides by a very particular number, and I can get rid of those fractions. So I'm going to multiply both sides by 4 times 5, which is 20. I've recognized I have a 5 giving me a fraction and a 4 giving me a fraction. So I'm going to multiply both sides of my equation by their product, 20. And when I do that, look what happens. I end up with something like this, right? And now when I do 20 times 3 over 4x minus 20, we'll go ahead and write out this step. And I have 20 times 7 over 5. Well, the 20 and the 4 can reduce to give me a 5. 20 over 4 is 5. Similarly, over here, the 5 and the 20 can reduce, and I just am left with 4, which means now I have 5 times 3x minus 20 equals 4 times 7. Basically, my fraction's gone away because 20 helped the denominators reduce away. So now I simplify this one more line. I get 15x minus 20 equals 28. And now I have something without any fractions in it, which is beautiful because nobody likes fractions. So now let's keep going, and we will add 20 to both sides. And we get 15x equals, and 28 and 20 is 48. So now I have x equals 48 over 15. And that can be reduced a little bit because notice they're both divisible by 3. 48 divided by 3 is 16. And 15 divided by 3 is 5. So 16 over 5 is what that reduces to. So your answer might have fractions in it, but very quickly, again, by doing this multiply by 20 trick, we were able to get rid of the fractions. So this next page allows us to check our answer. So I'm going to need to remember exactly what this problem was and what our solution was. So we had 3 over 4x minus 1 equals 7 over 5. And our solution was x equals 16 over 5. Is that correct? Yep. Okay. So with our problem and our solution, we can actually check our work by plugging in 16 over 5 in for x and seeing what we get. So that would look like doing 3 over 4 times 16 over 5 minus 1 equals 7 over 5. Well, that is 48 over 20 minus 1 equals 7 over 5. You know what? When I typically would write this down to, I wouldn't even write if it equals 7 over 5. I'm just going to do this calculation and see if it equals 7 over 5, just to keep my own notes a little bit clearer. So to evaluate 48 over 20 minus 1, I'm going to rewrite 1 in a common denominator by writing it as 20 over 20. And then I can easily do this fraction subtraction and get 28 over 20, which is, in fact, if I divide the top by 4, I get 7. If I divide the bottom by 4, I get 5. So we're good. We have checked that our solution of 16 over 5 does, in fact, give us the output 7 over 5. Now let's look at something like this, where we're just given the two expressions and we need to solve for x. The key thing here is to move all of your x values to one side and your non-x values to the other side. So to start, I'm going to subtract 1 from both sides. And I have 3x equals 2x plus 4. 5 minus 1 is 4. Now, like I said, I want all my x's on one side and non-x's on the other. So I'm going to subtract 2x from the right-hand side to move it to the left-hand side. And now I have x equals 4. Because immediately I'm left with 3x minus 2x gives me 1x. And I only have a 4 on the right-hand side. Therefore, we're done. That's actually it. But the key thing is actually moving the different components to the different sides. Now we can try to solve things graphically. So how we're going to do something like that, where if we have 3x plus 1 equals 2x plus 5, we're going to have our first value, or our first line, be the left-hand side, 3x plus 1, and our other line is going to be 2x plus 5. And when we graph these lines, we can actually look at where they intersect. Because the x value, where they intersect, is where we get that our y values match, which means that that is where these two are actually equal. So let's see how to do this on a graphing calculator. So here I am looking at my calculator, and what I'm going to do is go to the y equals. And under y equals 1, I'm going to plot my first value, which was 3x plus 1. So I go 3x plus 1. And under the other one, I'm going to graph the other value, which was 5x plus 2. Let me just double check that real quick. Yep. No, we had 2x plus 5. I'm glad I checked. 2x plus 5. So let me clear that out. We have 2x plus 5. Okay. Now I can look at the graph and I can see where they intersect. And I think my second line is actually cutting off a little bit. Oh, yeah. I thought that might cut off a little bit. We can't actually see the intersection point. So we're going to go to window, and I'm going to make my x min 0, and my x max, I'll leave it 10. And then my y min, I'll be at 0, because I'm kind of zooming in on that first quadrant, and I'll make the y max 15, okay? So this changes what axis I'm looking at. And so now I'll just be looking at the first quadrant, where my x values go from 0 to 10, my y values go from 0 to 15. When I look at that graph, let's see, there's our first line, and there's the second line. Now we can see where it intersects. Great. So now, if we want to actually have the calculator calculate that, what we can do is hit second, and we go to trace, which is calculate. And then we're going to scroll down to where we see intersect. I'm going to say enter. And it asked me, well, which one's the first curve? And I can't actually see what we're selected on. There we go. So now you can see as I move a little bit to the left, you see that I have a dot showing up on my first line. So I'm going to hit enter. And then it says, well, which one's the second curve? And it automatically highlighted my other line. So I hit enter again. It always asks this guess. We don't need to guess. So I hit enter one more time. And there we have it. It gave us the intersection is x equals 4 and y equals 13. And that's exactly what we got algebraically as well. So it's up to you. Sometimes it's easier to do it algebraically. Sometimes it's easier to do it graphically, where you just plot the two different sides of the equal sign as lines and see where their intersection is. Now back to the slides. as a recap, we could solve 4x minus 3 equals 2x plus 5 by just looking at the algebraic option or the graphic option. And either way, you're going to get 4, 13. So let's see a few more examples. And these are actually going to be a couple different special cases that you'll have to get used to. So like I said, I always want to move my x values to one side and non-x values to the other. So let's do that. Let's subtract 7 from both sides. And I get minus 24x equals 10 minus 24x. Now I'm going to add 24x to both sides. So I have all my x's contained on one side, not both. But look what happens. I have a minus 24x plus 24x, and that gives me 0. And I'm left with a 10 on the right-hand side. But 0 doesn't equal 10. This is certainly not true. So that means that there are no solutions. These two lines, this equation has no solutions. Now let's talk about what that looks like graphically. You might have noticed that the number in front of the x, which we usually call slope, is negative 24 in both cases. That means that we actually have parallel lines, because the 7 and the 17 also do not match, which means our y-intercepts are different, but they have the same slope. Therefore, we have parallel lines. And of course, parallel lines never intersect, so there is no solution. Now for the next special case, let's look at this one. What if I subtract 3 from both sides? Then I have negative 1/3 x equals negative 1/3 x. Okay, well, let me move my x's to the other side. And I'll then add 1/3 x to both sides. All right, move all my x's to the left-hand side. Well, then I end up with 0 equals 0, which is true, but where's my x value? Well, it fell away because everything just adds to 0. So in fact, all values of x are solutions. So it doesn't matter what x value I plug into this equation, I'm always going to have a true answer. So we say, my solution set is negative infinity to infinity. Graphically, this means that they are the same line. That in fact, on the left-hand side and the right-hand side, I have the exact same line. Now, zeros of linear functions. So any input x equals c of a function f is called a zero if the output is y equals 0. So we say c is a zero of f if f of c equals 0. So when you're asked to find the zero of some function, you're going to take that function and set it equal to 0 and solve for what input gives you an output of 0. Okay, so I'm going to set x squared minus 3x plus 2 equal to 0 and find out what value of x gives us the output of 0. We call that value of x the zero of f. So to solve something like this, I gotta factor first. I can't look at it just like this in the x squared terms. So I know I'm going to have an x in my first location. And now I got to think about things that multiply to 2. Well, I have a 1 and a 2 then, because 1 times 2 is 2. So that's the only thing that multiplies to 2. Now I got to think about my signs. I end in a plus 2, which means I have to have matching signs. They're either both negative or both positive. And here they must be both negative since I have a negative 3 in the middle. Now, when I have two things that multiply to 0, I set each thing equal to 0. and I end up with x equals 1 and x equals 2. Therefore, my solution set is both x equals 1 and x equals 2. I say solution set to when it equals 0. These are what we call the zeros of f, or function. And any linear function that has a non-zero slope has exactly 1, 0, always. Now, what this means graphically when we think about our intersections is that if we're looking at f of x equals 0, well, f of x is our first y, which means 0 is our right-hand side y. So y equals 0 is actually the x-axis. So really we're looking at, well, when does f of x cross the x-axis? So now we're kind of left with 3 names describing the same point, and I just wanted to throw that together for you guys, where whenever we're talking about the 0 of a function, that's the same thing as the x-intercept on a graph, which is the same thing to the solution to f of x equals 0. So I can ask it to you 3 different ways at this point, and you have to give me the same answer, set it equal to 0, and solve for x. Now you can also find the 0 on a calculator. So I'll show you how to do that with 5x minus 9. Here we are back at the calculator. I'm going to go to y equals, and we're going to look at 5x minus 9. Enter. I'm going to go to the graph, and we can clearly see it. Now we're also going to do, again, second calculate. And this time we're going to select the 0. And it says, well, where approximately on the left are we hitting? So basically I want to pick the left of the intersection I care about, and I hit enter. And then I go a little bit to the right, and I pick the right bound of the intersection I care about. And I say, find me the 0 between that left bound and right bound. So remember, something like a quadratic could cross the axis at 2 places. You got to specify which one you're looking for. So if I hit enter again, it highlights the 0 for me. It shows me x is 1.8 and y equals 0. So there's my solution. Back to the slides. So basically, when we have this, let me turn on my pen. When we have this x equals 1.8, that tells us that is the solution to 5x minus 9 equals 0. And you can check it, right? 5 times 1.8 minus 9 equals 0, and 5 times 1.8 is in fact 9. So you get 9 minus 9, which equals 0. Correct. Now, moving on. Applications using linear models. Mathematical techniques are used to answer questions arising from real-world situations. That's why we give you real-world problems all the time. Linear equations and functions model many of these situations. So before we jump into more problem solving in these word problems, we're going to start to really systematize how we think about problem solving. So this step 1 is going to have multiple parts. The other few steps are going to be the most natural part. But of course, interpreting the problem is always the hardest part. That's why we've broken out into these different steps. So we first want to familiarize ourselves with the problem. That means making a drawing, if possible, assigning our x and y variables to represent our unknown quantities. So I say, oh, x is my input, and that represents cost. And y is my output, and that represents profit. Right? You write these things down as sentences. And sometimes it makes more sense to use other letters other than x and y as well. The next step is to write down all the known facts about the problem. So what is all the information you're given? And what do you actually want to find out in order to answer the problem? Sometimes at this point it's helpful to draw a chart to help organize that information if it's appropriate. You also want to write down other information, so think about relevant formulas, like distance formula or midpoint formulas. You want to think about similar problems. that might be helpful, different things like that. And then you want to try to make a guess or an estimate about the answer. So you want to make sure I'm answering with a number, a point, an interval. And if it's a number, can I say, oh, it's somewhere in the ballpark of 10 and 30, not 10,000 and 30,000. That's what I mean by estimate. What kind of general range of numbers are we talking about here? Once you've done that, then you want to translate the problem into a mathematical language or symbol. You want to carry out as much of the mathematical manipulation as you can. Check your answer if you can to see if the solution actually works. And then state the answer clearly, ideally using a complete sentence. So let's see an example with the motion formula. The motion formula, or the distance formula, says a distance d traveled by an object moving at rate r over time t is given by d equals rt. So d is our distance, r is our rate, and t is our time. Okay. So the problem goes, Delta Airlines fleet includes a B737/800s with a cruising speed of 517 miles per hour, an SAAB 340Bs with a cruising speed of 290 miles per hour. Suppose that the SAAB takes off and travels at its cruising speed. 1 hour later, a B737 takes off and follows the same route, traveling at its cruising speed. How long will it take the B737 to overtake the SAAB? Well, let's see. We got to interpret all this information that we're given. So, familiarize yourself with the problem situation. Let's think about a drawing. And luckily, the textbook came with a drawing, so I didn't have to think about it myself. But we have the SAAB taking off first, and then the B737. And we're thinking about at what time do they actually match up, okay? That is what we're trying to picture in mind. When does that happen? So variables t and d, well, t, of course, is time, since, and we want to be specific here, the B737, I guess, /800 took off. Okay. Time when the B737 took off, because we want to know how long it takes the B737 to catch up. Now our distance d is the distance that they've traveled. Now, our known facts. Well, we know the SAAB has a 1 hour head start. And we also know that the SAAB 340B goes at a rate, actually I'll write it down, R equals, and I got to go back 1 second, 290 miles per hour. And the 737 has a rate of, come on, there we go, 517. Okay, so we have our two rates. And then we're looking for when the distance is the same. The distance traveled is the same. That's when we know that they line up. You could draw a chart here if you want to. I'm not going to worry about it for this problem. But for other formulas that we might want to know, we might want that distance formula, d equals r times t. And then if I had to guess, if I had to think about one plane takes off at 290 miles an hour, and an hour later, I have a second plane taking off at almost twice the speed, and it's really going fast in order to catch up that first plane, I'm going to guess that we're somewhere in the ballpark of like 1 to 5 hours before the Boeing catches up. I mean, it's going twice as fast as the first one. The whole point here is that you certainly shouldn't get an answer of something like 300 hours, right? That would be insane, an insane amount of time. We saw this drawing. So now we want to think about, okay, how do we translate this into using the formula D equals R times T? Well, for the Boeing 737, we'll start with this one first. We'll say D1 equals our rate 517 times our time. And for the SAAB 340, we know our distance is 290 times. Now, I don't have just time, right? Because this T is the time since the Boeing 737 took off. So, but this guy has been traveling for an hour longer than that. So this guy is actually at time plus 1 for 1 hour. Okay. So those are our two formulas that we're thinking about. And since we want to know when the distance is the same, we're actually just going to set these two, equal to each other. Okay. And that is what we're going to have to solve now. Wrong way. There we go. So we want to carry that out. 517 T equals 290 T plus 1. Okay, so I'm not going to do anything to the left-hand side yet, but I am going to distribute the 290. And it looks like that. And now I'm going to subtract 290T from my right-hand side, because as you know, I want to have all of my T values on one side. And we need to now do 517 minus 290, and that is 227. And I'm still left with 290 on the right-hand side. So now I divide both sides by 227. And I have T equals 290 divided by 227, which is about 1.28. Now, if we want to check that, remember our first distance was 517T. So that would be 517 times 1.28, which is, get the calculator, 517 times 1.28, 661.76. Now to check the other one, D2, which was 290 times T plus 1. Well, that's 290 times 2.28, right? 1.28. Let me write out those details. I don't want to confuse anybody. That's 1.28 being plugged in for T plus 1. So that's 290 times 2.28, which is 661.2. So you can tell they're very, very close, and that's just because I had to round to the 8. It actually kept going. But we have checked that we do, in fact, have the correct time. They have gone the same amount of distance at that time. So to sum it up and state it in a sentence, we want to say about 1.28 hours after the B737 is taken off, it will overtake the SAAB 340B. Now let's work on a different example, where here we have the simple interest formula. The simple interest I on a principal of P dollars at interest rate R for T years is given there. I equals PRT. And here is the write out of all those variables. So I is our simple interest, P is our principal, R is the interest rate, and T is time. So the problem goes, Demarian's 2 student loans totaled $28,000. One loan is at a 5% simple interest rate, and the other is at a 3% simple interest. After 1 year, Demarian owes $1,040 in interest. What is the amount of each loan? So let's familiarize ourselves with the problem. There's not much to draw here. There's no diagram we'd want to throw together, but we will want to think about our variables P and I. So P is going to be our principal amount. And I'm going to say it's the principal amount for the 5% loan. Because really we need to know that, and then we can actually figure out, well, what is the principal amount for the 3% loan? Because we know that they total $28,000. So P is the principal amount for the 5% loan. I is going to represent interest. Then we also want to note that we have an R, which equals our rate, and a T, which is time. But really, T is just always going to equal 1 for this problem. Because remember, we're talking about after 1 year. So time is just going to be 1. So we also know that the two interest rates of the two loans are 5% and 3%. The total borrowed is $28,000, and the interest after 1 year is $1,040. Now you can also draw a chart here to help organize those different things, but I'm going to move on to our formulas, and the formula we care about is I equals PRT. But to make this simpler, since our time here is always 1, we're just going to look at I equals P times R. Now, if I had to guess or estimate my answer, I'm not terribly sure. It's probably going to be something, it's definitely going to be a split of 28,000. Maybe I'll guess that it's going to be 12,000 for the 5% loan and like 16,000 for the 3% loan. But you know it's going to be some split of 28,000. So I certainly should not end up with an answer of 30,000 and 30,000, right, for my principal amount. That clearly does not total to the amount borrowed of 28,000. So we can at least guess that much. Now, let's try to translate it here. And instead of using this, we're really just going to use I equals P times R. Let's focus on the 5% loan first, because we said that the interest here is going to be our principal amount P, because that's the principal amount for the 5% loan, times 0.05. And we'll call that interest 1. And now for the 3% loan, I have I2 equals, and now thinking about, instead of plugging in P, because P is the principal amount for the 5% loan, well, that means that the principal amount for the 3% loan is whatever's left over of the 28,000. So that's 28,000 minus P. Okay, times its rate of 0.03%. Well, 0.03. So since the interest totals to $1,040, we know if we add these two equations together, we should get $1,040. So I get, let me write this in a normal order, 0.05 P plus 0.03 times 28,000 minus P. And that equals 1,040. So we've used the two rates. We used what we defined P as to get our principal amount for the 5% is just P. The principal amount for the 3% is 28,000 minus P. And we know those two interest amounts need to total to 1,040. So from there, we carry it out. So that was 0.05 P plus 0.03 times 28,000 minus P equals 1,040. Let me just check I didn't miss anything from the previous slide. No, that's perfect. Okay, let's carry this out. So it's 0.05 P plus 0.03 times 28,000. That seems to be 840. And then minus 0.03 P. Now I combine like terms and I get 0.02 P plus, let me not forget to write down the right-hand side there. Okay, so 0.02 P plus 840 equals 1040. So I subtract 840 from both sides, and I get 0.02p equals 200. And I divide by 0.02. P equals 10,000. All right, so 10,000. So that's our principal amount for the loan that's at the interest rate of 5%, which means for our loan, for the 3% loan, the principal amount is 28,000 minus 10,000, which is 18,000. Like that. You can check your work by plugging the p-value of 10,000 back into the formula. I'll let you do that on your free time. But to finish it out and make a statement, Damarian borrowed $10,000 at 5% interest and $18,000 at 3% interest. And notice it is a split of 28,000 between the two different ones. So we know that answer also makes sense. Okay. Moving on. So we are moving on to inequalities, and this is the start of section 1.6. All this previous material is in your textbook under section 1.5. So an inequality is a sentence with these different symbols as its verb. So for example, if I read this sentence, 3 times x minus 5 is less than 6 minus 2 times x. So to solve an inequality is to find all values of that variable that make the inequality true. Similarly to before, all solutions is called its solution set. And any two inequalities that have the same solution set are called equivalent inequalities. We have similar principles for solving inequalities. So if we have, again, our A, B's, and C's, we can add some value to both sides, and that is still a true statement. And then for multiplication, we have to be a little bit more careful. Because you might remember, if you multiply or divide by a negative number, you have to flip the sign. So if we have A is less than B, and C, I'm looking at this case here, and C is less than 0, so C is negative, then when we multiply both sides by a negative number, we have to flip the inequality. Quick example of that is if I subtract x from both sides, I get 2 is less than negative 4x. So if I'm trying to get the x alone, I have to divide by negative 4 on both sides. And I get negative 1/2 is greater than, because I divided by negative on both sides, x. Okay. So notice I had to flip my inequality from a less than to a greater than. So it's important that you keep that in mind. Similar statements all hold for less than or equals to as well. Now for an example, let's solve each of the following and then graph the solution set. So I have 3x minus 5 is less than 6 minus 2x. So let's add 5 to both sides. And I get 3x is less than 11 minus 2x. And I add 2x to both sides. And I have 5. I'm going to go to the next line. 5x is less than 11. And then I divide by 5 on both sides. I get x. Well, let's go ahead and use a new line. I get x is less than 11 over 5, which is about 2.2. So I'm going to graph this on the solution set. 11 over 5, which I guess is exactly 2.2. That I want to put on the number line. I have a less than, so I want to use an open circle somewhere around there. And I want to represent all numbers to the left of that. So that's shading all this to the left. Now in the next one, I'm going to add 4 to both sides. And I get 17 minus 7x is greater than or equal to 10x. I'm going to add 7 to both sides. I get 17x is greater than or equal to, adding 7x to both sides, I get 17 greater than or equal to 17x. So I divide by 17 on both sides, and I get 1 greater than or equal to x. Now, I find it less easy to read this. We're so used to reading this the other way around that I'm actually going to rewrite this by just reversing the order and making sure that the inequality is opening towards the 1 still. So I can see that this actually means x less than or equal to 1. Again, I find that easier than translate to the number line, because then I can just go, okay, I need to mark x at 1 and fill it in because we have an or equals to. And then I want to represent all numbers less than that. So again, I want to shade everything to the left of that line, of that dot. All right. Now, when two inequalities are joined by and or, by the words and or, a compound inequality is formed. So an example of one with and in it is called a conjunction, and you'd see it looks something like this. -3 is less than 2x plus 5, and 2x plus 5 is less than or equal to 7. But when we have an and, so a conjunction, we just write it in one line that has two inequalities for a shorthand, an abbreviation. On the other hand, we might have something that's a disjunction or an or in there. So x less than or equal to -7 or 2x greater than 1. So if we were to try to plot the disjunction on the number line, we'd have x less than or equal to -7. Okay, so I want, to plug in at -7. I fill it in because I have an or equals to, and I'm going to represent all numbers to the left of that because it's less than. Now 2x is greater than 1. We got to do one step to get the x alone here. We divide by 2 on both sides, and we see x is greater than 1/2. So I'm going to put an open circle where I have 1/2, and I'm going to shade all values greater than 1/2, which pushes off to the right. And you'll actually notice a pattern. Oftentimes when you get an or statement like that, you will have them going in opposite directions like that with a gap in the middle. So just keep note of that. So if we wanted to solve this and then graph the solution set, let's look at that. Basically, you're going to treat this as though we have 2 equal signs in here instead of 1. So in a sense, you're going to do something to every side of every equation. So starting off, if I want to subtract 5 from the middle to get the 2x alone, I'm going to subtract 5 from the right and subtract 5 from the left. And I get -8 less than 2x less than or equal to 2. Similarly, if I divide by 2 now, I'm going to do that to the right and to the left, and I get -4 is less than x less than or equal to 1. Now let's stick that on the number line. I have an open circle at -4, and I want to represent things that are greater than -4, numbers that are bigger than -4. Okay, so it's going to stretch to the right. But now I need to think about where I'm going to stop. Well, I need to mark 1, and I fill it in because I have an or equals to. And basically, I'm going to shade everything in between these 2 dots. Those are all valid solutions, valid x values that give us a solution here. Okay, for now a conjunction example, or a disjunction example actually, with an or in the middle. Basically, we're just going to carry out the same idea, and we're just going to do it twice. So I'm going to add 5 here on both sides, and I get 2x less than or equal to -2. And so if I divide by 2, I get x is less than or equal to -1. Now on this other one, 2x minus 5 is greater than 1. I add 5 to both sides, and I have 2x is greater than 6. So I get x is greater than 3. So that is my solution set. As a quick recap for interval notation, this would be negative infinity to negative 1 with a bracket, not a parenthesis. We have an or equals 2. So union, and then a parenthesis for sure, 3 comma infinity. That was our interval notation. Please review the worksheet from today if you need to see that again. So I'm going to mark negative 1 with a closed circle. I'm going to mark 3 with an open circle. I'm going to draw in then everything to the left of negative 1 to represent all numbers smaller than that off to negative infinity. And then I shade in all numbers to the right of 3. Again, going up to positive infinity. And as usual, the disjunction version of this with the or in the middle has a gap in the middle of our number line. That's just how they most of the time how they look. Now, I wanted to throw in this example because you actually have this on your homework that has several more terms in it, but we do the exact same thing. So let's do this example together. We are going to simplify both sides as much as we can, which means distributing this first term. Then we got to FOIL out the right-hand side. So starting with the distribution, we get 6x squared minus 12x, because I have 6 times x times 2, 12x, is less than, I'm going to leave the 3 there for a minute, and then I'm going to FOIL this guy. So first is 2x squared, outer is minus 6x, inner is a minus 1x, and then a plus 3. And now I have 6x squared minus 12x is less than, and now I'm going to distribute my 3. I'm also going to combine my like terms here in the middle. And we end up with 6x squared. Now, minus 6x minus 1x is a minus 7x, times the 3 is a minus 21x. Now plus 9. Now I'm going to move all of my x terms over to the left-hand side. So to do that, I'm going to start by subtracting 6x squared from both sides. And it turns out the 6x squareds completely fall away on the left-hand side. And I have a minus 12x less than minus 21x plus 9. So now I'm going to add 21x to both sides. And negative 12 plus 21 is 9x less than 9. Now I divide by 9 on both sides, and I get x is less than 1. So that complicated looking equation we originally given just simplifies down to x is less than 1. So I draw an open circle at 1, and I represent all numbers less than that. Now, I believe this is our last example, if I'm not mistaken. And it's an application of these inequalities that we've been working with. So, for her interior decorating job, Natalia can be paid in one of two ways. She can either be paid a $250 flat rate plus $10 an hour, or she can get paid $20 per hour. So how many hours does she need to work for plan B to be the better option? All right, let's go through our new framework for understanding word problems. So familiarizing ourselves, there's not really the need for a drawing here. We want to think about our variables. We'll call them n and p. I'm going to say n is the number of hours. And we'll say p is the pay, total pay. So our known facts, well, we know that plan A is $250 fixed plus $10 an hour, and plan B is just a $20 an hour. You could draw a charter table here if you want to. But otherwise, I want you to be thinking about, for further info, other linear problems we've done. Whenever we had a fixed price on something plus a price per something else, think about what that typically looks like and where our fixed cost goes versus where our per hour cost goes. And then we can guess or estimate the answer, and I don't know, it's somewhere in the range of in the tens of hours, right? I shouldn't get an answer with 3,000 hours in it ideally. I think it'll make sense for this to catch up somewhere between 10 and 30 hours, but we'll see. So we need to translate this to our symbols now. Pay from plan B is greater than the pay from plan A. So if N is our number of hours, the pay from plan B, going back, $20 per hour. So remember, N is the number of hours. And so our pay from plan B, I'll just use a subscript B, is 20 times N. Now we got to think about the pay from plan A, which is, going back a slide, $250 fixed plus $10 an hour. So when we write this down, we write down the fixed cost, $250, and then we add on $10 times the number of hours. And so we want to know when plan B is greater than plan A. We want to know when 20N is greater than 250 plus 10N. So let's carry that out. So I'm going to subtract 10N from the left-hand side, from both sides, to move it to the left-hand side. And we have 10N is greater than 250. Now I divide both sides by 10. And I get N must be greater than 25. Okay. So now we can check if we work, let's say 26 hours. Because we need to pick something. So remember, we got N is greater than 25. So what happens if we work 26 hours? Or if, what is her name? Natalia works 26 hours. Well, then plan B, which was $20 per hour, becomes 20 times 26, which is 520. Yeah. Whereas plan A, which was 250 plus 10N, well, that's 250 plus 10 times 26. That's 250 plus 260, whoops, which is $510. So yep, at 26 hours, she made more doing plan B like expected. So there we checked our work. Again, I just picked an arbitrary value above 25 just to see that plan B made us more money, made Natalia more money. And so to state the final answer, once Natalia works more than 25 hours, plan B is better for her. And that's it. So thank you so much for joining the lecture video today, and reach out if you have any questions.